Okay, welcome back to the deep dive. Today we're doing something a bit different. Instead of chasing the latest headlines, we're digging into the backstory of something that feels intensely current: machine learning.
That's right. We're going deep into the history of ML, and it's a fascinating story, often quite surprising.
Yeah, it's easy to just think, oh, Silicon Valley, recent tech boom,
Hmm.
but the roots go way, way back
Yeah,
to places and ideas you might not expect at all.
exactly. We're drawing from the complete history of machine learning here, trying to pull out the really key moments, the kind of forgotten figures, the twists and turns.
Right. So you, the listener, can really get a sense of how this field, which is, changing everything today, actually got started.
And spoiler alert,
Mhm.
the starting point is pretty far removed from the tech giants we know now.
Okay, let's get into it then. Let's rewind way
Yeah.
back. Where does the ML story really begin? Not with code and servers, but the core ideas.
Well, it starts with this incredible collision, really. A mix of different fields. You've
Mm.
got mathematics, neuroscience, even psychology, and the very, very early days of computer science.
Wow.
And the initial goal, it was hugely ambitious. It wasn't just about building a gadget. It was about trying to understand and then actually replicate the computational power of the human brain itself.
Mimicking the brain.
Yeah.
That's not what I would have guessed. So less about solving a specific task, more about understanding intelligence.
Precisely, at the very beginning. And a really foundational moment happens way, way back, 1943.
Yeah.
You have Warren McCulloch, he was a neuropsychiatrist, and Walter Pitts, this mathematical whiz kid. Together, they created the first mathematical model of a neural network.
1943, that's wild. Feels like a different universe. So what was the breakthrough there? What was the big
The
idea?
really audacious part was the idea that something as complex, as mysterious as human thought, maybe it could be broken down, reduced to logical operations, performed by networks of really simple computational units. They were building on Alan Turing's theoretical work on computation, basically showing that simple things, connected like neurons, could do complex stuff.
And they actually modeled a neuron, like a simple artificial one.
Yes, and it was beautifully basic. It had inputs, right? Each input had a weight, sort of like connection strength. Then there was a threshold.
Uh-huh.
If the total weighted input crossed that threshold, bang, it produced an output, a binary output like fire or don't fire.
Like a simplified brain cell.
Exactly. Based on what they understood about biological neurons then. And that simple model, honestly, it laid the conceptual groundwork for modern neural networks. It's the ancestor.
Okay, now this is where it gets really interesting for me.
Hmm.
Because just 7 years later, 1950, the man himself, Alan Turing, pops up again,
Right.
asking that incredibly simple but impossibly deep question: can machines think?
And crucially, he kind of sidestepped the whole messy philosophical debate about consciousness. What is thinking, really?
Smart move.
Yeah. He proposed a practical test instead. Basically, if a machine could chat with a human, and the human couldn't reliably tell if it was a machine or another person.
Then for our practical purposes, it could think.
Exactly. We should just consider it capable of thinking. Pragmatic.
The Turing test.
Yeah.
That must have just completely shifted the focus for people who are in this area,
Oh,
right?
absolutely.
Maybe less about trying to perfectly copy biology and more about copying the behavior.
You got it. It gave the field this, like, a North Star, a concrete goal, even if it wasn't perfect. It moved AI research from being purely philosophical speculation into something you could actually try to build and test.
Okay, and then things started moving faster. Because 1952 seems like another big step.
Yes, right on the heels of Turing's paper. This is Arthur Samuel at IBM. He created something genuinely revolutionary for the time.
What was it?
A computer program that could learn. It played checkers. But the key thing was, it wasn't just programmed with fixed rules, it got better. It improved its game through experience.
Okay, wait. And this is where the actual term machine learning comes from. Samuel coined it.
That's the story, yes.
Mhm.
He's credited with coining machine learning to describe this ability programming computers so they can learn from experience. And think about how revolutionary that was.
Yeah,
A machine acquiring skills, getting better through practice, kind of like how we learn.
and the source mentions something about how much better it got.
Right. It played thousands and thousands of games against itself, just practicing, analyzing positions, outcomes, refining its strategy.
Wow.
By the late 50s, it wasn't just good, it was beating Samuel himself, its creator. And other strong human players, too. Imagine that, teaching a machine to school you at checkers just by letting it practice.
So, okay, we've got the math model of a neuron, we've got the Turing test as a goal, and now we have the first program that actually learns. That must have lit a fire under people.
Absolutely. The late 50s, early 60s, this was a period of intense optimism, maybe a little too much optimism in hindsight.
Right.
And this really came to a head at the 1956 Dartmouth Conference.
Ah, yes. The famous birthplace of the term artificial intelligence.
Exactly. John McCarthy coined the term there. He brought together all these big names, Marvin Minsky, Claude Shannon, Alan Newell, just luminaries.
And they thought they were close.
They thought they were really close. The feeling was, get a small group together for a few months, focus hard, and they can make massive breakthroughs, maybe even crack general AI.
Just months. Wow. Talk about ambition.
Huge dreams. Their vision wasn't small scale. They were talking machines that could use language naturally, understand abstract concepts, solve complex problems, even improve themselves. Essentially, building artificial minds.
And hot on the heels of that conference, in '57, came a machine that seemed like it might actually deliver on that promise. The perceptron.
Frank Rosenblatt at Cornell.
Yeah.
The perceptron is often called the first algorithm that could learn directly from data. And importantly, it wasn't just theory they built it. Actual hardware, the Mark I perceptron.
A physical machine that learns patterns.
Right. It could learn to recognize simple visual patterns, classify inputs based on the examples it was shown, and the reaction. Well, the public and media reaction was, let's say, enthusiastic.
Uh-oh. Hype train incoming.
Full steam ahead.
Yeah.
The New York Times famously reported on its potential. Future versions, they speculated, might walk, talk, see, write, reproduce itself, and be conscious of its existence.
Okay, that's ambitious. Conscious. Wow, that sounds awfully familiar, that level of hype. Is that a pattern we see repeating?
Oh, definitely. The perceptron hype is a classic example, and it's a recurring theme right up to today. The core idea behind the perceptron was powerful showing machines could adjust automatically based on experience,
Right.
but the public imagination, and maybe even some researchers, just ran miles ahead of what it could actually do at the time.
Were there other related things happening around then, too? Building on these ideas?
Yeah, people were definitely exploring variations. You had Bernard Woodrow and Ted Hoff developing Adeline. It used a slightly different learning rule, could handle continuous values, not just on-off, and Oliver Selfridge's pandemonium architecture. Looking back, it seems really prescient. It used these parallel daemons or detectors, kind of anticipating some ideas in modern deep learning.
So things seem to be rocketing forward. Thinking machines felt just around the corner. What went wrong? What stopped the momentum?
Well, here comes the crash. The first major reality check, the first AI winter starts to set in around 1969.
What triggered it?
A book. A very influential book by Marvin Minsky and Seymour Papert called simply Perceptrons. And it wasn't just a review, it was a deep mathematical takedown. They proved rigorously that these single-layer perceptrons had fundamental limitations.
Limitations how?
They simply couldn't solve certain types of problems that seem pretty basic. The most famous example is the XOR function, the logical exclusive OR.
Wait, not being able to do something as simple as XOR?
Yeah.
That was enough to derail the whole field.
It sounds small, but it was seen as exposing a really critical fundamental flaw in that whole approach. If it couldn't handle XOR, how could it handle truly complex problems? The conclusion many people drew was, this whole neural net idea, it's a dead end. And the consequences were pretty drastic. Funding dried up, interest just evaporated. Neural network research basically died for almost 2 decades.
Wow. So neural nets go into hibernation. Where did the AI researchers turn their attention during this winter?
The field mostly pivoted. It shifted towards what's called symbolic AI. That became the dominant paradigm for a long time.
Symbolic AI, what does that involve?
It's about building systems that manipulate symbols and rules, basically, trying to explicitly encode human knowledge and reasoning processes into computer programs.
Like those expert systems you sometimes hear about, capturing the doctor's knowledge or something.
Exactly like that. And they had some real successes, some commercial applications in narrow fields, but they had their own problems. They were often very brittle.
Brittle, meaning?
Meaning they worked okay within their specific domain, but couldn't really learn or adapt if they encountered something outside their pre-programmed knowledge. They couldn't handle ambiguity or new situations well.
So not really learning in the way Samuel's checker player did.
Not really. Machine learning, in that sense of systems learning from data and experience, it really did go into hibernation during that period.
But hibernations don't last forever, right?
Yeah.
When did the thaw start for neural networks?
A renaissance? Yeah, it began quietly. In the 1980s, there was a small group of researchers who kind of kept the faith. People like Jeffrey Hinton, David Rumelhart, Ronald Williams. They kept working on neural nets, specifically focusing on networks with multiple layers.
Okay, multiple layers. And what was the key? What allowed them to overcome the limitations that Minsky and Paper pointed out?
The key was an algorithm called backpropagation. They refined and really popularized it between about 1982 and 1986. It provided an effective way to actually train these deeper multi-layer networks.
So how did backpropagation crack the code? How did it solve the XOR problem, for instance?
Well, having multiple layers, those hidden layers between input and output, allowed the network to represent more complex, nonlinear relationships, the kind of thing XRR needs. Backprop gave them the mechanism to adjust the weights in those hidden layers. It works by figuring out the error at the very end, at the output, and then propagating that error signal backwards, layer by layer.
Ah, backpropagation. Makes sense.
Exactly. It figures out how much each connection, each weight contributed to the error, and adjusts it to try and do better next time.
And was this a totally new idea or?
Not entirely. Similar mathematical ideas had actually surfaced earlier, but they were either forgotten or maybe the computers weren't powerful enough to make them practical.
Right.
The big difference in the 80s was computational power. It was finally becoming feasible to actually run backpropagation on these multi-layer networks. The hardware was catching up to the theory.
Interesting. And wasn't there another slightly different kind of network that emerged around then too?
Yes, John Hopfield introduced Hopfield networks in 1982. These were different. They weren't really general-purpose learning machines in the same way. They functioned more like an associative memory.
Associative memory,
Yeah.
like our brains.
Kind of. The idea was you could store patterns in the network. Then if you gave it a partial pattern or a noisy version of a stored pattern, the network could sort of settle into the closest complete clean pattern it remembered.
So it could like fill in the blanks or clean up a fuzzy memory. That's cool.
Oh, it is cool. And it was important work. It provided a solid theoretical foundation for how networks could store and retrieve information. It also brought in ideas from physics, statistical mechanics, showing these interesting cross-disciplinary connections.
And then, in 1986, we get a program that learned something, well, something very human.
Terry Sejnowski's NetTalk.
Yep.
Yes. This was really compelling. It was a program that learned to pronounce written English text out loud.
Okay, how? Did they program in all the pronunciation rules?
No, that's the amazing part. It wasn't explicitly programmed with rules like I before E except after C. It learned purely by example. It was shown pairs of written words and the correct phonetic pronunciations.
And it learned like a baby learns to talk.
That was exactly the analogy everyone drew. It started out making random noises, basically babbling, but gradually, just by being exposed to the examples and using backpropagation to adjust its internal connections, it learned to pronounce words quite coherently.
Wow. That must have been a powerful demonstration.
Hugely powerful. It showed convincingly that neural nets could tackle complex real-world tasks, learning directly from data, not just following pre-programmed instructions.
Okay, so the 80s brought neural nets back from the cold, thanks to backprop and demos like NetTalk. What defined the 90s then? Did things accelerate?
The 90s saw another important shift. Machine learning started becoming much more mathematically rigorous, more grounded in statistics. This is sometimes called the statistical learning revolution.
Statistical learning. So less about mimicking the brain maybe, and more about the pure math of learning from data.
For a while, yes, that was a major focus. There was a move towards algorithms that had really strong theoretical foundations, provable properties.
Like what?
A prime example is support vector machines, or SVMs. Introduced by Vladimir Vapnik and his colleagues around the mid-90s. SVMs were mathematically elegant, had these nice theoretical guarantees, and worked really well in practice on many problems.
Okay.
And alongside specific algorithms like SVMs, this period saw the real development of formal statistical learning theory. This gave researchers frameworks to understand why algorithms worked, how well they would generalize to new data.
Introducing core concepts we still use all the time.
Absolutely. Things like the bias-variance trade-off, the importance of cross-validation for evaluating models, techniques like regularization to prevent overfitting. These became central pillars of the field and still are.
And wasn't this also when the idea of combining multiple models took off?
Definitely. Ensemble methods really came into their own. Leo Breiman's random forests from 1995 is a classic example.
Random forests, right. How do they work?
The core idea is surprisingly simple but powerful. You build not just one decision tree model, but lots of them, a whole forest. Each tree is built on a slightly different subset of the data or features. Okay? Then, to make a prediction, you get a vote from each tree in the forest, and the majority wins. The key insight is that combining many weak learners, even if each individual tree isn't perfect, can create a single, much stronger, more robust predictor overall.
That makes sense. Strength in numbers.
Exactly. And other ensemble techniques like boosting, developed by Freund and Shapire, also became really important around this time.
And crucially, the 90s seems to be when ML starts to actually leave the lab and
Yeah,
get a job,
right.
starts showing up in industry.
That's a perfect way to put it. This is absolutely when we see the rise of ML in industry. Companies started realizing these techniques could solve real business problems.
Like what kind of things? Early days, but still.
Think early recommendation systems.
Yeah.
Customers who bought this also bought on sites like Amazon, maybe early Netflix recommendations.
Oh, okay.
Improving search engine results, Google was founded in '98, leveraging these ideas. Use in finance started picking up algorithmic trading, credit risk assessment.
So it was shifting from this cool academic pursuit to a genuinely useful, practical tool,
Precisely. That transition was key in the '90s.
which sets the stage for the 2000s. What catalyzed the next big leap forward? You called it the data revolution earlier.
Yeah, two massive forces converged in the 2000s. First, remember those neural networks. The quiet progress hadn't stopped. In 2006, Geoffrey Hinton published some really key papers.
Hinton again. What was the breakthrough this time?
He showed new techniques, ways to effectively train deep neural networks with many, many layers using methods like layer-by-layer pre-training.
And this is the real beginning of the deep learning revolution we hear so much about.
This is really where it kicks off in earnest, yes. The crucial insight or demonstration was that these deep networks could learn hierarchical representations of data automatically.
Hierarchical, meaning layers of understanding.
Exactly. For images, say, the first layer might learn to detect simple edges. The next layer combines those edges to find corners or simple shapes. Layers above that combine shapes into object parts and then whole objects like faces or cars. The network figures out these features itself at different levels of abstraction.
Wow, okay. That sounds powerful. And the second force you mentioned?
Data. Unimaginable amounts of data. The internet exploded in the 2000s. Think digital photos, web pages, social media posts, online shopping, search queries.
A digital tsunami.
Absolutely. And this flood of data was the essential fuel. These deep data-hungry models needed massive data sets to learn effectively. The more data, generally, the better they performed.
So data became the new oil, as they say, for machine learning.
It's a very fitting analogy, and companies sitting on huge data sets, think Google with all its search and web data, were suddenly in an incredibly powerful position to build new kinds of systems.
And this leads us to a really critical development for making progress measurable, right? ImageNet in 2009.
Yes, ImageNet was huge. Fei-Fei Li and her team at Stanford had this vision. They created this enormous database, over 14 million images at its peak, all carefully labeled with categories, like this picture contains a cat, a dog, a car.
Why was having one big labeled data set so transformative?
It did a couple of things. First, it provided the scale of data needed for deep learning models in computer vision. Second, and maybe more importantly, it created a standardized benchmark, a common challenge.
Like a yearly competition for vision algorithms.
Exactly. Everyone could test their new ideas on the same massive, difficult data set and see how they stacked up. It turned computer vision research from, maybe researchers working on their own little data sets into a more systematic science. You could objectively compare methods.
And that competition must have driven progress like crazy.
Incredibly rapid progress. It really set the stage perfectly for the 2010s, which is when deep learning just explodes into the mainstream.
Right, the deep learning explosion. And the absolute pivotal moment seems to be 2012. AlexNet.
AlexNet, yep. Led by Alex Krzyzewski, working with Ilya Sutskever and, yes, Geoffrey Hinton again. They built this deep convolutional neural network, entered it into the ImageNet competition. And it didn't just win, it destroyed the competition. Its error rate was dramatically lower than the second place entry, which was using more traditional computer vision techniques.
Now, that must have sent shockwaves through the field.
Complete paradigm shift. It was undeniable proof. Deep learning wasn't just promising, it worked spectacularly well on really hard problems like image recognition that had stumped researchers for decades.
The reaction from industry.
Immediate. Every major tech company saw that result and basically said, we need to be doing this. Investment in deep learning research just skyrocketed overnight.
And part of the reason this became possible then, not earlier, was hardware, right?
Yeah.
Something maybe already sitting in people's gaming PCs.
The GPU revolution, exactly. Graphics processing units. GPUs were designed for rendering complex 3D graphics in video games, which involves doing tons of matrix calculations in parallel. And it just so happens that training neural networks also involves tons and tons of matrix calculations that can be done in parallel. GPUs were accidentally the perfect hardware.
A happy accident.
A world-changing happy accident. Companies like NVIDIA, who made GPUs, suddenly found themselves at the center of the AI revolution. Their CUDA platform made it easier for researchers to harness GPU power for computation, not just graphics.
So the hardware and the algorithms finally clicked perfectly. And the mid-2010s just seemed like a whirlwind after that, breakthrough after breakthrough.
It really felt like that, just an incredible pace of innovation. 2014, you get generative adversarial networks, GANs, from Ian Goodfellow.
GANs,
Yeah.
those are the ones that can create realistic images and stuff.
Exactly. A completely novel way to train models to generate new data that looks real images, music, text, mind-blowing stuff.
What else?
Also in 2014, sequence-to-sequence models really took off, transforming machine translation and text generation. Suddenly, computer translations started getting actually useful. 2015, you get ResNet residual networks. They introduced this clever skip connection idea that allowed researchers to train incredibly deep networks, like over 150 layers deep, without performance degrading.
And that pushed image recognition even further.
Pushed it past human-level performance on the ImageNet benchmark, a huge milestone.
And then 2016, the moment that really captured the public imagination, maybe more than anything else.
AlphaGo. DeepMind's AlphaGo defeating Lee Sedol, the world champion Go player.
Why was that such a big deal? We already had chess computers.
Go is just vastly more complex than chess. The number of possible game positions is astronomical, more than atoms in the universe. Experts genuinely thought mastering Go was decades away for AI.
So AlphaGo's win was a shock.
A profound shock. It showed the power of combining deep learning with reinforcement learning in a way that just stunned people.
Okay, so incredible progress. And then around 2017 comes another really fundamental piece of the puzzle, especially for language.
The attention mechanism.
Yes.
Yes. Primarily from the Google Brain paper titled, famously, Attention is All You Need.
Attention. What does that mean in this context?
Traditionally, models processing sequences like sentences would look at words one after another. Attention allows the model to weigh the importance of all the words in the input sequence simultaneously, figuring out which words are most relevant to understanding or generating the current word.
So it can focus on the important context wherever it is in the sentence.
Exactly. It gives the model a much better sense of long-range dependencies and context. It was revolutionary for language tasks.
And this led directly to
The transformer architecture. That paper introduced the transformer built entirely around attention mechanisms. It became, and still is, the dominant architecture for large language models.
like GPT and BERT.
Precisely. Models like GPT from OpenAI, BERT from Google, and countless others are based on the transformer. It's incredibly effective, and its design also allows for much more parallel processing during training, which is crucial for building these massive models.
Which brings us neatly into the current era, the 2020s. Dominated by these huge models and, well, a lot of talk about AGI, artificial general intelligence.
Absolutely. The language model revolution really bursts into public view in 2020 with OpenAI's GPT-3.
What was so special about GPT-3?
Its sheer scale, primarily. 175 billion parameters, which was unprecedented at the time. And that scale led to something fascinating. Emergent capabilities.
Emergent capabilities, meaning it could do things it wasn't explicitly trained to do just because it was so big and had seen so much data.
Basically, yes. Just by scaling up the model and the data, it started exhibiting abilities like writing surprisingly coherent essays, generating working code, composing poetry, holding conversations that felt remarkably fluid, things that smaller models just couldn't do.
It feels like a real shift.
It was. It signaled a move away from AI systems designed for very narrow, specific tasks toward systems that felt, well, more generally capable.
And then, late 2022, the floodgates opened with ChatGPT.
That was the moment AI truly went mainstream for the public. Its conversational interface was so easy to use. Millions of people suddenly started interacting with a very advanced AI daily. It wasn't locked away in labs anymore.
And the impact was immediate.
Yeah.
Seems like it triggered a new, very intense AI arms race.
No question. And it really cemented the era we're in now, which people are calling the foundation model era, roughly 2023 onward.
Foundation models. Explain that term.
It refers to these extremely large pre-trained models. Could be language models like GPT-4, could be vision models, could be multimodal models handling text, images, audio all together. They're trained on vast, diverse data sets.
Okay.
And the idea is you treat these as general purpose foundations. Instead of building a specialized AI from scratch for every single task, the new approach is often to take one of these huge foundation models and then fine-tune it, adapt it for your specific application.
That completely changes how AI gets built and used. It's a different paradigm.
It really is.
So looking back over this whole epic journey from McCulloch and Pitt's simple neuron in 43 to these massive foundation models today, what are the big themes, the recurring patterns that the source material really highlights?
Yeah, the source points out several really important patterns that help make sense of it all. One, undeniably, is the cycle of hype and disappointment. AI winters.
We definitely saw that with the perceptron, right? And
Right.
the expert systems later.
Exactly. The early enthusiasm runs way ahead of the actual capability, leading to disillusionment, funding cuts, the winter. Then quieter progress happens in the background, eventually leading to a new spring, often with even more hype. Understanding this cycle is crucial for keeping perspective today.
That's a great point. Another theme seems to be the absolute necessity of computational power.
Oh, absolutely critical. So many breakthroughs weren't just about a new algorithm. They were about an algorithm finally becoming practical because the hardware caught up.
Right. Perceptrons hit limits in the 50s. Backprop needed 80s computers.
And the deep learning explosion of the 2010s was completely reliant on GPUs and cloud computing power becoming available and affordable.
Which suggests future leaps might depend on new hardware again. Quantum, maybe?
Neurons,
Neuromorphic
yeah.
chips.
It strongly suggests that, yeah, hardware advances have consistently unlocked algorithmic potential.
And the third big theme, we discussed data. Data as the fuel.
Can't overstate the importance of the internet creating this ocean of data. Modern ML, especially deep learning, is incredibly data hungry. That data infrastructure is just fundamental.
But it also raises huge questions, right? Privacy, bias in data, who owns it, who benefits.
Massive questions. As the source implies, those are some of the defining challenges that come along with this data-driven power. They're social and ethical questions as much as technical ones.
And the last pattern. This wasn't built in a vacuum. It wasn't just computer scientists.
Not at all. It's always been incredibly interdisciplinary. You had mathematicians, neuroscientists, psychologists involved right from the start. Later, physicists contributed ideas.
And that cross-pollination seems key.
Often, the biggest breakthroughs happen at the intersection of fields. People bringing different perspectives, different tools. And that's only accelerating now, pulling in biology, chemistry, materials science.
It's easy to get lost in the tech, the algorithms, the data, the hardware. But reading through this history, it's so clearly a story about people. Specific individuals with brilliant, sometimes unconventional ideas.
Absolutely. It's driven by human ingenuity and persistence. You think about the folks who stuck with neural networks through those long AI winters when everyone else said it was a dead end.
Like Walter Pitts, the prodigy working on that first model back in the 40s.
Right. Or Arthur Samuel, who not only built that learning checkers program, it actually gave the field its name.
And Geoffrey Hinton, the godfather of deep learning, his persistence is just incredible, championing neural nets for decades.
And Fei-Fei Li, whose vision for ImageNet really catalyzed the whole computer vision revolution.
Plus Hinton, Jan LeCun, Yoshua Bengio, the Turing Award winners, whose foundational work underpins so much of modern AI.
Exactly. These are people who had a vision, who were persistent, willing to challenge the status quo, often facing skepticism. Their contributions are immense.
They really steered the ship. So we've traced this amazing arc from an abstract mathematical idea about neurons to technology that, billions of people interact with daily now. It's staggering.
It really is an astounding intellectual journey spanning, 80 years now?
Yeah.
Full of brilliant insights, frustrating setbacks, surprising breakthroughs, and ultimately incredible progress.
And the source makes it clear this story is far from over, right?
Not even close. Today's large language models, the multimodal systems, they feel incredibly advanced. But history teaches us this is likely just the current chapter. Maybe a very exciting chapter, but still just a chapter.
So understanding this history isn't just academic. It helps us evaluate what's happening now.
Definitely. It gives you context. It helps you maybe separate the hype from the reality. And it reminds us that progress hasn't been linear or predictable. Big breakthroughs often come from unexpected directions.
So wrapping this up, what's the big takeaway from this deep dive into ML history? Where does it leave us?
Well, the history makes one thing crystal clear. The question is no longer if machines can learn. They demonstrably can. They're getting astonishingly good at it.
Right.
The real questions now, especially as these foundation models get more powerful and we start thinking seriously about AGI, the questions are what will they learn to do next? And maybe the most crucial question of all, how will we as humans learn to adapt, to coexist, to thrive in a world where powerful machine intelligence becomes truly ubiquitous?
That is definitely something to chew on. What an incredible journey through the past to understand our present and maybe glimpse the future. Thanks for unpacking that.
My pleasure. It's a story worth knowing.